Hello, this is Mrs. Huntley. This is Module 4, Lesson 22. You should have your module open to Lesson 22, Constant Rates Revisited. Your essential question for this lesson: when I'm writing an equation for a constant rate problem, how do I know which situation has a greater or lesser rate of change? So first of all, this is kind of a review. Off the beginning of this module, we were setting up equations for word problems, word situations, and most of those were constant rate type things. So this is going back to one of the earlier lessons, but now we're going to do more with the equation once we get it set up. So let's talk about constant rate. What is our definition for constant rate? Constant rate is the average rate that somebody does something over an extended period of time. So if we're talking about driving a car and we say we're going 45 miles per hour and it's at a constant rate, we're assuming that 45 miles per hour is not going to change regardless of the time period that we're driving. Synonyms for constant rate: slope. We've been talking about slope a lot. Rate of change. I'm talking about that as well. Constant proportionality is more last year, probably what you talked about last year with your proportions and your constants. So let's look at the first example. Erica set her stopwatch to 0 and switched it on at the beginning of her walk. She walks at a constant rate of 3 miles per hour. Express this as an equation, table of values, and graph. So x is going to be time. X equals time. And y is going to be our distance. And we walk 3 miles per hour. So distance over time, remember this, 3 over 1. So our rate of change is 3. If I were putting this in equation, I would say y, total distance, equals 3 times the amount of time you're traveling. So this is my time. This is my distance. So if I have not been walking for any time at all, I've gone 0 distance, right? And they gave us the one at 1 hour, she travels 3 miles. So at 2 hours, we can plug it into the equation. 3 times 2 is going to be 6. And then at 3 hours, I don't know if we even need to plug it into the equation. I will, though. Y equals 3 times 3. That's going to be 9 miles. If I'm graphing this, now nothing's going to go negative because I can't have negative time and I can't have negative distance. So 0, 0 is right smack in the middle. And then 1, 3, come over to 1 and then up 3. Oh, I wrote the wrong number in here. I'm sorry. This should be a 6. 2, 6, and then of course 3, 9. Now if we're looking at our graph, you know what, I'm going to go ahead and connect these with a straight line because this would represent any time interval. So like in an hour and a half, I'd be going about, I don't know, what is that, about 4 miles-ish? But I can figure out any time interval using my graph. And what I want to show you is that my rate of change, or my slope, is represented on the graph too, because I go up 3 units and right 1, up 3 units, right 1. So that's how these 3 things, the equation, the table, and the graph, are showing you the same thing. Now I can write the equation from the story problem, I could write the equation from a table, and I can write an equation from a graph. So either way, all 3 of these things are representing this equation. Let's look at the next example. A faucet leaks at a constant rate of 7 gallons per hour. Suppose Y gallons leak in X hours from 6 a.m. So let's take a look at this. Y is our gallons. X is our time. Right now they're telling us that it's 7 over 1. That's our rate of change. That's our slope. So when I'm writing the equation, y equals, I can say 7 over 1 or just plain old 7, x. So however many time or however long it's leaking for, that's what I would plug in for x, multiply it by 7, and that will give me the total amount that is leaking. So the slope represents the rate at which the faucet is leaking. Okay. Another faucet leaks at a constant rate, and the table below shows the number of gallons Y that leak in X hours for 4 selected hours. So 13 is leaking in 2 hours. So how could I figure out how much is leaking in 1 hour? I can take that 13 and divide it by 2, and I'm going to get 6.5 in 1 hour. So I can say my rate of change here is 6.5 gallons per hour. And I want to make sure, and so if I'm writing this equation, I'd have y equals 6.5x, and x would be the number of hours. I want to make sure that my unit measure, like per hour or whatever, is the same when I'm comparing things, because if it's not the same, then I don't know, because saying 13 gallons in 2 hours and trying to compare that to 7 gallons in 1 hour, it'd be hard to make that connection of is one greater than the other. Whereas if we have it the same time interval, the 1 hour, it's easy to see that the second faucet is leaking at a slower rate because my slope is less. 6.5 is less than 7. So that's what I'm going to be comparing when I'm trying to determine which one is leaking quicker or slower. So the first faucet leaks at a faster rate. So if something is leaking at a faster rate, it has a larger number representing the slope or the rate of change or the constant proportionality, however you want to express that. Okay. So the key is, however our data is being represented to us, whether it's in a table or whether it's in words, we're going to create an equation and we're going to compare the slopes. Next page. We have a train. And let's take a look at how fast this train is traveling. This is my hours. My x is my time in hours. My y is my distance. That makes sense. And let's see, it's passing an integer coordinate here. In 1 hour, it's going 60 miles. So this train A, I want my distance over my time, or y over x. So it's going to be 60 over 1. So if I'm writing that in an equation, it's going to be y equals 60x. I can plug in any time and find out how far this train is. Train B travels at a constant rate also. The train travels at an average rate of 95 miles every 1.5 hours. Write an equation that represents the constant rate for train B. So again, I need to make sure my time interval is the same, because I could represent this as 95 over 1.5, but it's going to be hard to compare my two trains. So I'm actually going to do the division here. 95 divided by 1.5 is going to give me a weird repeating decimal, but that's okay. We're going to go for it. 63.3 miles per 1 hour. So I can write my equation as 63.3 times x. I could also have written my equation as y equals 95 divided by 1.5x. That's not incorrect, but again, my comparisons are much more difficult when I don't have the same unit. So, which one has a greater rate of change? Train B has a higher rate of change or slope, which means it's traveling at a faster rate of speed per hour. The next question says, why do you think the strategy of comparing each rate of change allows us to determine which train is traveling at a faster rate, greater speed? The slope represents the constant rate in a specific time interval. If the time interval is the same, whichever is greater is going to be faster. Go ahead and pause the video if you need to, but I'm going to move on to example 4. Example 4 represents the constant rate at which Christina can paint. So we've got time in minutes going across the bottom, that's our x, and area painted in square feet going up the y. So in 1 minute, Christina is painting 4 feet. Okay, so if I'm writing this equation, I would say y equals 4x, and x is the number of minutes. I could say 4 over 1x, that's fine. Christina's sister, Tracy, paints at an average rate of 45 square feet in 12 minutes. Assuming Tracy paints at a constant rate, determine which sister paints faster. So I'm going to take my 45 feet in 12 minutes, and I'm going to figure out how fast she paints in 1 minute. So I'm going to do that division. 45 divided by 12. It's going to be 3.75 in 1 minute. So when I'm writing this equation, it's going to be y equals 3.75 x. So Christina paints 4 feet per minute. Tracy paints 3.75 feet per minute. Which one's faster? Christina. How does the slope provide information we need to answer the question about which sister paints faster? Slope is the constant rate. In 7th grade, you learned it as a constant of proportionality, but that's telling us how fast or how slow something is done in a given time interval. Okay, example 5. The graph below represents the constant rate of watts of energy produced from a single solar panel produced by company A. So we've got our time in hours on the x, and we've got watts produced as our y. Find some integer coordinates, and it looks like it's going to be 120 watts per hour. So y equals 120 x, because that's per 1 hour. So company B offers a solar panel that produces energy at an average rate of 325 watts in 2.6 hours. So I'm going to take my 325, divide by 2.6, so I can see how much per hour, and I'm going to get 125 in 1 hour. So if I'm writing that equation, it'd be y equals 125x. So assuming solar panels produce energy at a constant rate, determine which company produces more efficient solar panels. That's more energy per hour. So if 125 is greater than 120, company B is producing at a higher rate. Compare the slopes. The slope represents the constant rate of change. If you're looking for one that produces at a greater rate, you want the greater slope. You're going to have to be cautious to make sure that you're reading the problem carefully. If you're looking for a situation in which the cost is less or it changes more slowly, you might be looking for a smaller slope. But here, I'm going to choose company B because company B has a higher rate of change per hour. Okay. The other thing to be careful of is make sure you're comparing your apples and apples. So this is 125 per hour, 120 per hour. Exercises 1 through 5. I'm going to do, let's see. Yeah, I'll go ahead and do you know what I would like you to do? Pause the video and see if you can work some of this out on your own, and then unpause the video to check your progress. So Peter paints a wall at a constant rate of 2 feet per minute. Assume he paints an area y in square feet after x minutes. Express this situation as a linear equation in 2 variables. So pause the video and see if you can get this equation written. Okay, 2 feet per minute, so that's going to be 2 over 1. So total feet, y, is equal to 2 feet times the number of minutes. So that'll be your x. I guess you don't have to put that in parentheses, do we? Okay. Sketch the graph of the linear equation. If you need to do a table, you can. I don't think that you should have to, I wouldn't think. Now notice that the area in square feet, they're counting by 2 here, and the time in minutes, they're only counting by 1. So if I'm going up 2 and over 1, I'm going to be hitting every one here. Even though that looks like a 1 over 1 slope, it's because our graph is going up by 2 in that direction. So use the graph or the equation to determine the total area he paints after 8 minutes. So I can keep going here. And at 8 minutes, I'm looking at 16. Okay. 1.5 hours and 2 hours. So again, remember that hours are 60 minutes. So we're going to, and that's our time interval here. So we're going to need to convert 1.5 hours equals how many minutes? So 1.5 times 60, that's going to be 90 minutes. And 2 hours equals 120 minutes. Now that's not easily found on our graph, so I'm going to use the equation. So y equals 90 minutes, so 2 times 90. So that's going to be 180 feet, 90 minutes. And then y equals 2 times 120. So that's going to be 240 feet in 2 hours, or in 120 minutes. Okay. Okay. Although we're doing well on time, I'm going to go ahead and end the lesson here, and we're going to do the next few problems together in class tomorrow. So your general strategy for comparing proportional relationships to determine which one is going faster and which one's going slower is to put it into an equation and compare the slopes, or compare the rate of change. Make sure, some things to be cautious about, make sure that the time interval is the same when you're comparing two rates. And I'm going to conclude the lesson here, and we will see you in class tomorrow. Have a good night. Bye.